Hi everybody, it's Professor Mitchell. Today we're starting what might be my favorite chapter, Chapter 4 on number theory. And in this first section, we're going to look at divisibility. Students will be able to understand and explain divisibility, factors, and multiples. We'll talk about divisibility tests for 2, 3, 4, 5, 6, 8, 9, 10, and 11. And that the set of factors is finite and the set of multiples is infinite for any given natural number. All right, so first of all, as you know, an integer is even if it has a remainder of 0 when divided by 2. Now, this is probably not the way you think about even numbers. You think of even numbers as 2, 4, 6, 8, 10, 12. Well, when you divide any of those numbers by 2, you get a remainder of 0. And if an integer is not even, it's odd. We say that 3 divides 18, which we write like this, because the remainder is 0 when 18 is divided by 3. I think this came up in the last section of Chapter 3. Likewise, B divides A can be written like this. We say that 3 does not divide 25, which is written like this, because the remainder is not 0 when 25 is divided by 3. So here is the definition for any whole numbers A and B, where B is not 0. B divides A if and only if there is a unique whole number Q such that A is equal to B times Q. So this reminds me a little bit of the division algorithm from the last section of Chapter 3. Remember, the division algorithm said that for any whole numbers A and B, there exist whole numbers Q and R such that A equals BQ plus R. So this is just talking about the case where R is 0. So this is just saying that A is evenly divisible by B. That's another way of saying that. If B divides A, then B is a factor or a divisor of A, and A is a multiple of B. Lots of vocabulary at the beginning of a new chapter. All right, so here we have some true or false statements, starting with 3 divides 12. So remember what that means. If there is a whole number that makes 12 equal 3 times that number, let's call that number Q. If there is a whole number such that 12 equals 3Q, then this is going to be a true statement. And it's true, right? Because there is a number like that. It's called 4. However, this statement here, 0 divides 2, we'd be looking for a number Q that makes 2 equal to 0 times Q. So that's not going to work, right? So letter A is true, letter B is false. Continuing, the number 0 is even. Is that true or false? Sometimes this one's a little controversial. Well, even means if you divide it by 2, the remainder is 0. Well, 0 divided by 2 is 0. That's the quotient. And there is no remainder. So 0 is an even number. All right, I personally find these ones a little confusing. Any true-false statement that has the word not in it is bound to be a little confusing. So the statement is 8 does not divide 2. If you prefer, you can think of the statement as 8 divides 2, and then we'll just change, if it comes out true, we'll change it to false. If it comes out false, we'll change it to true. So if 8 were to divide 2, that means there would be a whole number that makes 2 equal to 8 times Q. Well, there is a number like that, but it's a fraction. It's not a whole number. So the statement 8 divides 2 is false, which means 8 does not divide 2 is true. So these two statements are both true. All right, continuing, for all whole numbers A, 1 divides A. When you divide any number a by 1, what do you get? You get a, and you don't get a remainder. So that is a true statement. Ooh, this one looks tricky. For all non-zero whole numbers a squared divides a to the 5th. Well, luckily, I think it was the last couple of sections of chapter 3, we talked about exponent rules. So let's see what we know about a to the 5th divided by a squared. A to the 5th divided by a squared. Remember, that's called the quotient rule for exponents. So that's the one where you subtract the exponents. A to the 5th divided by a squared would be a to the power 5 minus 2, which is a to the 3rd. Is that a whole number? Well, if a is a whole number, then a to the 3rd is definitely a whole number. This is true. All right, 3 divides 6 times n for all integers n. 6n divided by 3, that would be 2n, wouldn't it? And there wouldn't be a remainder. So that's true. Oh, there's more. Okay, this one I've been thinking about a little bit. This one might be the hardest one so far. And I don't know what happened to the lettering. I just noticed that. This one here should be letter I. So the statement is 3 does not divide the number 5 times 7 times 9 times 11 plus 1. Okay, I decided it might be a good idea to switch over to the tablet for this one. So the statement was true or false, 3 does not divide 5 times 7 times 9 times 11 plus 1. So let's think about this. The question is, when you divide the number 5 times 7 times 9 times 11 plus 1 by 3, do you get a remainder? So hopefully I'm not cheating here and using too many things we haven't talked about, but I don't really know how else to do this, other than multiplying the number out and adding 1, and that doesn't seem like any fun. So what I'm going to do is I'm going to break this into 2 fractions. The first one is going to be 5 times 7 times 9 times 11 over 3, and the second one is going to be 1 over 3. All right, so now look at what I notice. We can take this 3 and this 9 and divide out a 3, and that's going to leave 1 and 3. So that's going to leave me with 5 times 7 times 3 times 11 plus 1/3. And what that means is when you divide 5 times 7 times 9 times 11 plus 1 by 3, the quotient is 5 times 7 times 3 times 11, and the remainder is 1, this one here. All right, so since there's a remainder that is not 0, that means 3 does not divide that number, and this statement is true. So let's switch back. And there we go. Oh, look, this changed to an I by magic. All right, so that's true. Now this one's kind of tricky. I just want to go back, just so you know I'm not cheating, to the definition of divides. B divides A if and only if there is a unique whole number Q, such that A equals B times Q. So here's where that word unique really makes all the difference. So you could start off, we're on letter I, by asking, is there a whole number that makes this 0 equal this 0 times Q? Well, yeah, there are a whole bunch of numbers like that, right? You can put any number you want in there. But that number is supposed to be unique, which means this statement is false. 0 does not divide 0. 0 actually does not divide any number. All right. Properties of division. For any whole numbers a and d, if d divides a and n is any whole number, then d also divides n times a. So what this says in English is that if d divides a, then d is also going to divide all multiples of a. If d is a factor of a, then d is a factor of any multiple of a. For any whole numbers a, b, and whole number d with d not equal to 0, if d divides a and d divides b, then d divides a plus b. If d divides a and d does not divide b, then d is not going to divide a plus b. If d divides a and d divides b and a is greater than or equal to b, then d is going to divide a minus b. If d divides a and d does not divide b and a is greater than b, then d does not divide a minus b. So basically what a and c are saying is that if d divides a and d divides b, then d is going to divide the sum and the difference of a and b. And then letter B and letter D are saying that if it doesn't work for one of those numbers, then it's not going to work for the sum or the difference. Let's see. This almost says the same thing as letter D, almost. Letter D is talking about the second number in the difference, and letter E is talking about the first number in the difference. Okay, so more true or false. Classify each of the following as true or false, where x, y, and z are whole numbers. First one is if 3 divides x and 3 divides y, then 3 divides x times y. Well, that is true because, and actually they've given me more information than I needed, x times y is automatically going to be a multiple of x. So actually, as long as I know that 3 divides x, it doesn't even matter if 3 divides y. As long as 3 divides x, 3 is going to divide any multiple of x. And xy is a multiple of x. So that's true. Now, letter B seems familiar, right? We just looked at a bunch of statements that said something like this. In fact, let's go back here for a second. Almost looks like letter A of the properties of division, which said if D divides A and D divides B, then D divides A plus B. What this is saying is if 3 divides x plus y, then 3 divides x and 3 divides y. So if you think all the way back to logic, when was that? The beginning of chapter 2? This statement almost looks like the converse of that property B, all right? And what we learned in the logic section was that the converse of a statement is not equivalent to the original statement. Now, this statement might be true. I'm just saying it's not automatically true. And actually, this statement is false. And to convince you that it's false, I'm going to give you a counterexample. Let's make x equal 4 and y equal 2. That means x plus y will be 4 plus 2, which is 6. And 3 does divide 6, so that's true. However, 3 does not divide 4, and it does not divide 2. So this is a false statement. It would work if going the other way, if 3 divides x and 3 divides y, then 3 divides x plus y. That's true. That's one of the properties, but it doesn't work going the other way around. And letter C is also false. Can you think of a counterexample for letter C? How about 6? 9 does not divide 6. However, 3 does divide 6. Okay. Let's see, would that work the other way around? If 3 does not divide A, then 9 does not divide A? I think that one might work. Yeah, I'm pretty sure that works. If 3 does not divide A, then 9 does not divide A. I think it works going that way. Sometimes it's useful to know if one number is divisible by another just by looking at it. So that's where divisibility rules come in. For example, to check the divisibility of 1,734 by 17, we note that 1,734 is equal to 1,700 plus 34. We know that 17 divides 1,700 because 17 divides 17, and 17 also divides any multiple of 17. And also, I mean, it's pretty easy to just do in your head 1,700 divided by 17 is 100, right? Okay. Furthermore, 17 divides 34. Therefore, we conclude that 17 divides 1,734. Okay, but that's not typically what we mean by divisibility rules. I think more about this kind of thing. Starting with divisibility by 2. A whole number is divisible by 2 if and only if its units digit is divisible by 2. That is, if and only if the units digit is even. So if your number ends with 2, 4, 6, 8, or 0, I don't care how many digits that number has, that number is going to be divisible by 2. Whole number is divisible by 5 if and only if its units digit is divisible by 5, which means its units digit is 0 or 5. So if a number ends in a 0 or a 5, I don't care if it has 68 digits, that number is divisible by 5. And then the last of the super easy divisibility tests, a whole number is divisible by 10 if and only if its last digit is 0. Let's just cut to the chase. So these are the divisibility tests that go by only the last digit. If the last digit is 24680, then the number is divisible by 2. If it's a 0 or a 5, then it's divisible by 5. And if the last digit is a 0, then the number is divisible by 10. All right, continuing with divisibility tests. A whole number is divisible by 4 if and only if the last 2 digits of the number represent a number divisible by 4. So we'll get into official examples here in a little bit, but the number 17,268. Since that number ends in 68, you just have to look at 68. And since 68 is divisible by 4, 68 divided by 4 is 17. That means that the number, whatever I said, 17,268 is divisible by 4. All right, and then there's a similar test for 8. It goes by the last 3 digits. All right, a whole number is divisible by 8 if and only if the last 3 digits of the whole number represent a number divisible by 8. So take the number 1,674,800. Because that number ends in 800, that number is divisible by 8. Okay, so let's look at examples of some of those tests. Determine whether the number 97,128 is divisible by 2, 4, and 8. And I can tell you from experience, when you see a problem like this, it is not asking you whether the two numbers 97 and 128 are divisible by 2, 4, and 8. That is one single number there, all right? So that number is divisible by 2 because it ends in an 8, and of course 2 divides 8. It is also divisible by 4 because 4 divides 28. 28 divided by 4 is 7. And it's divisible by 8 because 8 divides 128. 128 divided by 8 is 16, right? All right, here's another example. Maybe you should pause the video and try this one. Determine whether 83,026 is divisible by 2, 4, and 8. It is divisible by 2 because 2 divides 6. However, it is not divisible by 4 because 4 does not divide 26. When you divide 26 by 4, you're left with a remainder of 2. And by the way, that automatically means that this number will not be divisible by 8. 8 does not divide 26. All right, this is a Venn diagram showing the relationship between numbers divisible by 2, by 4, and by 8. The numbers divisible by 8 are a subset of the numbers divisible by 4, and the numbers divisible by 4 are a subset of the numbers divisible by 2. That's how I knew that this number, 83,026, was not going to be divisible by 8 as soon as I saw that it was not divisible by 4. All right, if I were to place that number in this Venn diagram, it would be out here somewhere. It is divisible by 2, but it's not divisible by 4, therefore it can't be divisible by 8. All right. Continuing with divisibility tests, now we get into the really interesting ones. These ones are a little magical, I think. It's kind of hard to see why they work. A whole number is divisible by 3 if and only if the sum of its digits is divisible by 3. So take 83,026. 8 plus 3 is 11, plus 2 is 13, plus 6 is 19. So that number would not be divisible by 3 because 19 is not divisible by 3. And there's a similar test for 9. A whole number is divisible by 9 if and only if the sum of its digits is divisible by 9. So take the number 1002. Is that number divisible by 9? And well, by 3 and by 9? It is divisible by 3 because 1 plus 0 plus 0 plus 2 is 3. And of course, 3 divides 3. However, it is not divisible by 9 because 9 does not divide 3. The sum of the digits of this number is still 3. Therefore, 3 does divide 1002, but 9 does not. All right, here is another example. Try this one yourself. Pause the video. Determine whether 14,238 is divisible by 3 and by 9. The sum of the digits is 18, and 3 divides 18. Therefore, 3 divides 14,238. And 9 also divides 18. Therefore, 9 also divides 14,238. All right, here's a really fun problem. Store manager has an invoice for 72 calculators. The first and the last digits on the receipt are not legible. All the manager can read is that the total was something 167 and 90 something cents. And the question is, can we determine what those numbers are? What are the missing digits and what is the cost of each calculator? So let's represent the missing digits by X and Y so that the number is X 67 and 90 Y dollars, right? Which is this number of cents, X679Y. Okay, because 72 calculators were sold, the amount must be divisible by 72. Now, I'm trying to decide if the next thing that I'm about to tell you is, well, I'll just go ahead and tell you. Because they're not exactly telling you the whole story here. Because 72 is 8 times 9. Oh, no, I'm sorry. This is correct. Because 72 is equal to 8 times 9, the amount has to be divisible by both 8 and 9. Okay? So let's think about our test for divisibility by 8 and 9. Starting with 8, for the number on the invoice to be divisible by 8, the 3-digit number 79Y must be divisible by 8. So if you look at all the numbers between 790 and 799, the only one of those that's divisible by 8 is 792. Oh, remember the mental math tricks that we talked about in the last chapter? The reason that I know 792 is divisible by 8 is because it's 800 minus 8. 800 divided by 8 is 100. 8 divided by 8 is 1. That means 792 divided by 8 is 100 minus 1, which is 99. So that means y has to be 2. So we know it's some dollars and 92 cents. So now let's go after the value of x. Because the number on the invoice must be divisible by 9, we know that 9 must divide x plus 6 plus 7 plus 9 plus 2, which is x plus 24. And remember, x has to be a number really between 1 and 9, I guess. And the only number that's going to work for x is 3. That would make x plus 24 equal to 27. 3 is the only single digit that will make x plus 24 divisible by 9, so x has to be 3. That means the number on the invoice must be $367.92. And because there were 72 calculators, each calculator cost $367.92 divided by 72, which is $5.11. So these are pretty cheap calculators, actually. All right, and that brings us to a test for divisibility by 11. I did not learn this one when I was in school. I learned this one much later. It's a little bit more complicated than the others. It's not as complicated as they're making it sound, though. A whole number is divisible by 11 if and only if the sum of the digits in the places that are even powers of 10 minus the sum of the digits in the places that are odd powers of 10 is divisible by 11. So I'm going to put this a lot more simply for you. If you take the number and break it up into its digits and then go plus, minus, plus, minus, plus, minus, plus, minus, plus, etc. with those digits, look at that number, the answer to that problem, and if that number is divisible by 11, then the original number is divisible by 11. Okay, and then I'm surprised they waited so long to tell us about this one. I definitely do remember learning this one in school. An integer is divisible by 6 if and only if the whole number is divisible by both 2 and 3. So if it's divisible by both 2 and 3, then it's divisible by 6. So that brings us to this one last big example. We're going to determine whether, let's see, what is that number? 57,729,364,583 is divisible by each of the following. So clearly, it's not divisible by 2 because it ends in a 3. Let's see, is it divisible by 3? If we add all these digits together, 5 plus 7 is 12, plus 7 is 19, plus 2 is 21, plus 9 is 30, 33, 39, 43, 48, 56, 59. And 59 is not divisible by 3. So this original number is not divisible by 3. It's not divisible by 5 because it doesn't end in a 5 or a 0. And it's not going to be divisible by 6 because it's not divisible by both 2 and 3. A no for just one of these would make it a no for 6. It's not divisible by 8. It can't be. It's not even divisible by 2. Okay. Or you could take the number 583 and try to divide it by 8. It is not going to work. Is it divisible by 9? Well, those digits added up to 59. 59 is not divisible by 9. It wasn't divisible by 3 either. It's not divisible by 10 because it doesn't end in a 0. Okay, so now I finally get a chance to explain to you the test for 11. So I'm going to start over here, and I'm going to say 5 minus 7 is negative 2. Plus 7 brings me back to 5. Minus 2 is 3. Plus 9 is 12. Minus 3 is 9. Plus 6 is 15. Minus 4 is 11. Plus 5 is 16. Minus 8 is 8. Plus 3 is 11. And of course, 11 is divisible by 11. So this number is divisible by 11. And that's going to do it for section 4.1. We'll see you next time.